Okay. Thanks for attending my talk. This collaboration started with when I discussed with Sioli and Daniel Genkin and Yuval how we can mitigate Rowhammer attacks, but all in all, we just found another flip in the wall of Rowhammer defenses. So what is Rowhammer about? We already heard that in like 3 talks ago. It's about DRAM, and today if we look at DRAM, it's organized in channels, in banks and ranks. And if you look at one of those banks in detail, you'll find that this has several rows, many rows, and these are the actual capacitors in the rows, like 64,000 capacitors. These store the actual bits in your memory. And when you read from memory, the memory controller actually has to load the actual bits into the row buffer. That happens in the DRAM, and then it's sent to the memory controller, to the CPU. There is an effect that leads to the so-called Rowhammer effect, which is that cells leak fast upon proximate accesses, and we're going to exploit that. So if you activate those rows, after a while, you will see bit flips. There are different directions that we can now go. The first is, how do we do eviction? And there are a lot of papers going in different directions here. We've just seen one in earlier talk. But there's also another direction. How do we actually hammer? And previously, there have been 2 techniques known. The first is we hammer one row next to a victim row and other random rows, or we hammer 2 neighboring rows. And it looks like this. So if we do single-sided hammering, we just hammer a bunch of rows and expect bit flips next to one of them. In case of double-sided hammering, we are hammering 2 rows and we're expecting the bit flips, for instance, between those 2 or directly next to one of them. The question then is how to mitigate Rowhammer, and there have been a bunch of proposals how we mitigate Rowhammer attacks. For instance, detecting Rowhammer attacks via performance counters, because they have way more cache misses and cache hits than other attacks or other benign workloads also. So we can probably single them out. The other idea was, another idea was to detect them before they actually happen, for instance, using static analyzers on the binary and finding that there is such attack codes. There is, of course, an open problem, the false positives, but we will see another problem in a minute. There have been software-based defenses like Anvil. I'm just picking a few here. Anvil uses performance counters to detect which rows are hammered and then refreshes the neighboring rows. This also is available in hardware in a similar variant. Then it's called target row refresh. There was at Usenix last year BCAT and GCAT, and there the idea is to either disable the vulnerable physical memory locations or to isolate them, so to place some barrier, physical barrier between the different security domains. In that paper, it was just kernel and user space, but in general, you could do that with more security domains, of course. So if we put all of that together in a table, we see that we have a lot of defenses that use performance counters. We have a lot of hardware modifications. I didn't discuss them, and we will also not focus on them because most of them are not applied yet on current systems. And a few other static analyzers, physical proximity, memory footprint. So also the memory access pattern plays a role here. And the question, one of the core questions when we started was, do you actually have to hammer multiple memory locations? And that brought us to one location hammering. Actually, there are at least 3 different hammering techniques because we propose a third one. And there you only hammer one row and expect bit flips right next to it. Works like this. You hammer it, you activate it, it's deactivated, you activate it again, it's deactivated, you activate it, and after a while you see bit flips next to it. Why does this work? Because we heard in the previous talk that there was a system which used open page policy, probably. The idea there is that you keep the row open and buffered, and then you have a low latency for subsequent accesses to the same row, but a high latency for accesses to any other row. But there are thousands of different rows, so this is good if you're pretty sure that you're going to access the same row again. More efficient if you're expecting that the next access goes to a different row is the closed page policy. There you immediately close a row and are ready to open a new row, so you have a medium latency for accesses to any row, including the row that you have just opened before. So it's just a trade-off in this case. It has been found that these perform better on multi-core systems because there you have the memory accesses from different cores, and usually they are not so much related to each other. If we look at the bit flip distribution on a 4 kilobyte page, you can see that most of the bit offsets are covered. So we ran this test only for 8 hours, but basically you can reach any bit offset on a 4 kilobyte page with double-sided or single-sided hammering. With one location hammering, the number of bit flips is just lower. That's why we only have 36% of the bit offset covered after 8 hours. The distribution of 0 to 1 flips and 1 to 0 flips is approximately the same for all methods. So next question is, how do we exploit random bit flips? And we already heard that in the previous talk. They are not actually random. They are highly reproducible. Once you have a bit flip from some memory hammering pattern, you can reproduce it. So the strategy is always the same. You choose a data structure that you can place at an arbitrary memory location. Then you scan for good bit flips, and then you place the data structure there. Then you trigger the bit flip again, and then you have your bit flip in the right location. Previous defenses suggested that you could just make the kernel out of reach, right? Like the GCAT countermeasure. For that, we came up with some technique called opcode flipping. And with opcode flipping, we found that many applications on your system run as root. For instance, sudo runs as root, because they have to do some operation that unprivileged users cannot, but unprivileged users can use those applications. For instance, ping and mount also. We target sudo because it's easy to exploit. It's straightforward. If there's something wrong in sudo, then we might be root. And to illustrate what happens or might happen in the sudo binary, we will look at a jump equal instruction. And if we flip a bit in a jump equal instruction, it will change the semantics of the program. And if the right bit flips, it changes the semantics in a way that you can directly bypass the password check. This is quite unfortunate. Let's see whether we can actually have a bit flip in exactly that location. First, we don't need to target exactly that location. We can have a bit flip somewhere else in a binary as well. For instance, comparisons, addresses of memory loads and stores, address calculations. There are loads of different opportunities what you can flip. In a manual analysis, we found 29 possible bit flip offsets, but we think that we should automate this search for possible bit flip offsets, but we haven't done that yet. All of these bit flips somehow skip the password check, so somehow we can become root without knowing the password. The question now is, sudo, well, it's a binary, right? How do we get the target virtual page from this binary to the target physical location where we can induce the right bit flip? And for that, we introduce a technique called memory waylaying. The idea is quite straightforward. Basically, we want to maneuver a target binary page to a vulnerable physical page. And it's not as easy as with page tables or other pages that we can spray over the entire memory, because binaries are only once in memory. They are kept in the page cache. Once they are in the page cache, they will stay there. Even after the program terminates, the page will still be there. So when is it evicted? Only if the page cache is full. Only if the entire memory is full and the page cache has to remove one page to load one more page into the memory. The page cache usually occupies all the unused memory, so we would have to occupy all memory to throw out our page. However, instead, we can also just move the victim page to a target page by occupying the memory with other page cache pages. So we are evicting the page cache by filling it with other page cache pages. With that, we can evict the victim binary. And we can use mincore, that's a quite convenient system call for that, to check whether the victim page was evicted. So we just load more binary pages into the system, into the DRAM, until our victim page was evicted, and then we reload the victim and see that it has a new physical page. We continue with this until it's on the target page, and then we can induce our bit flip there. So just to illustrate this a bit, we start with maybe a memory layout like this. The blue parts are occupied, the white parts are free, and the gray parts are occupied by the page cache. Our binary page is marked as green with a B, and our target page is the X. And then we evict the page cache, so our binary page is gone. We reload it. We repeat this again and again until it's located at the right offset. How well does this work? Well, it's first of all system dependent. It depends on where the operating system, which pages the operating system assigns to your new page. On a default Ubuntu setup, we got this. So most of the physical memory was covered with that. So we were able to maneuver our page to virtually any physical memory location. The great advantage over just evicting the memory with a large array, with occupying just memory with our own data, is that we have a very negligible memory footprint. As you can see, the memory footprint stays very, very low because the page cache pages are not considered our pages. They are just system pages, right? And now the third step that we introduce is we combine Rowhammer with SGX, and we get two things out of that. The first is cheap denial of service. SGX is an instruction set extension, and it provides integrity and confidentiality for code and data in untrusted environments. You can run it as a regular user program, but you cannot perform certain things so that you're not able to implement malware in it, right? The enclaves use a dedicated memory area in the physical memory, the EPC region, and this is integrity checked and encrypted. So the question then is, what happens if a bit flips in this integrity checked region, right? And of course, the integrity check will fail. What will happen next? We lock up the entire memory controller, which is not a good idea, right? Because no further memory goes through the memory controller. The system halts immediately. I don't know, think of backing up some stuff before halting the entire system. Yes, sounds unsafe. It is unsafe. You will lose data if that happens. And we were able to trigger that. Actually, the first attack implementations we had triggered that by accident. We were not intending to trigger this in the beginning. Quite annoying if your system halts all the time. So the next thing is what if this happens in the cloud, right? If a malicious enclave does that in the cloud, for instance, Microsoft now has a cloud that allows you to use SGX. If we trigger that in the cloud, the entire machine halts, including the co-located tenants. So this is cheap denial of service attacks in the cloud, and you can do that again and again every time the system is booted up again. The other option that we can do is we can combine SGX with one-location hammering and opcode flipping and build an undetectable Rowhammer exploit. Because SGX protects software from malicious environments. It also protects it from some attacks like performance counter-based attacks. Most performance counters do not work on SGX enclaves. They are just not included in the performance counters. And this defeats quite a lot of countermeasures that rely on performance counters. Putting it all together, we can see that static analysis, performance counters are both defeated by using Intel SGX. One-location hammering destroys previous assumptions about the memory access patterns. Opcode flipping works around the physical proximity issue, and memory waylaying solves the problem that you have to acquire a lot of memory and by that bring your system close to out-of-memory situations. And by that, we have defeated all the different defense classes. With that, I will get to the conclusion, and the conclusion is it's easy to break previous assumptions, and that this is possible shows that we have an incomplete understanding of the attacks. We first need to get a more complete understanding of the attack before we are able to design complete countermeasures. The current countermeasures were only patches against specific exploit. They were not really solutions to the underlying problems. And as we heard in the previous talk already, it's quite difficult to solve the problem because in the end it's an optimization problem. On the one side, you want to optimize for performance. On the other side, you want to not have Rowhammer bit flips. The problem is that the attacker becomes more and more powerful. So attacks that were once not possible because the boundary was chosen wisely might become possible in the near future. And also, new features might introduce new attack vectors, especially the combination of SGX and Rowhammer here allows to change the nature of the attack quite a bit. Thanks for your attention, and I'm looking forward to discussion.
All right, amazing work, Daniel. Again, questions, please approach one of the mics and state your name and affiliation. Don't all run at once, though, because we don't want to flip any bits. Okay, go ahead.
Youngjun Jang from Oregon State University. So I have seen some of the differences based on the performance counter, and then by design, Intel SGX prohibited reading up the direct value. But there is a side channel tag on we can get some of the performance counter unit value from the uncore performance monitor, and then by subtracting some of the values, then we can indirectly know about what SGX has performed. And did you have any concern on that kind of the things could reveal, let the defenders can exploit that features?
Mm-hmm. Yeah, thanks for the question. Actually, we looked at quite a lot of performance counters, something like 40 to 50 different performance counters, and including also the uncore, for instance, the CBO cache events. And I'm sure there are performance counters which would work and which could be used to detect this attack, but we haven't found any. But probably there are. There's an abundance of performance counters. I'm not sure whether this is the right way to solve this problem because you can induce bit flips quite quickly in a small amount of time, and also our assumptions that Rowhammer so the attacks that we've seen today are still sort of local attacks, right? Because they have local code execution. But there is an upcoming ViewSec paper that shows that you can do Rowhammer attacks over network.
Thank you.
Yes, Matt.
Matthew Hicks, Virginia Tech. So yeah, you mentioned the upcoming packet-based, network-based Rowhammer attack we saw earlier. You can have, system on chip, kind of GPU-based, other, Rowhammer attacks. You see in this work a very systematic destruction of existing defenses. So where are you, and you said, I want to start out doing defenses. Where is your current mindset, your group's mindset on defenses now? Does it have to be hardware? Is there any hope for software? Where are you at on that?
It's quite difficult because I think we need a solution that is also backed by hardware mechanisms. A pure software solution probably would not work against the Rowhammer problem.
Then this challenge of deployability comes into play. What about all the systems that exist? How can we provide protection? Do you see a way forward for existing deployed systems?
Luckily, many systems seem unaffected, where many is something between 30 and 70%, because we don't have any good prevalence studies on Rowhammer. But most systems are probably unaffected, especially by the more exotic variants like Rowhammer and JavaScript. I'm not sure about the GPU variant because I haven't looked at the details. Probably this one is a bit more realistic, but for Rowhammer JS, your system has to be really, really susceptible for Rowhammer bit flips from JavaScript using the CPU cache eviction. Probably with the GPU it works a bit better. For in general, like the Rowhammer attack, that also requires RDMA. Most systems today don't have RDMA. So I would expect that most systems today are not immediate attack targets, not that much high on a target list of an attacker. Also because we have more easy vectors to get into a system, right?
Okay, we got two final questions. Ruby?
So, nice work. Now, SGX didn't have in its threat model either side channels or denial of service attacks. But of course, if the side channel does threaten loss of confidentiality or integrity, which is what SGX is trying to protect against, then that would be serious. But I guess all you showed was a denial of service attack, which is interesting, but you didn't get any loss of confidentiality or integrity, right?
So for the first attack, we had a denial of service attack, but the second one, where we combine it with opcode flipping and memory waylaying, for this variant, we actually compromised the system. The
integrity.
The integrity. So basically, we compromised the system. We can take full control of the system, not over the SGX part. This will still be protected.
Yeah.
The key point that we try to make here is that if you build SGX in a very clever way so that you cannot spy on benign applications, you also won't be able to spy on our Rowhammer enclave. So SGX then also protects our malware.
Right. I thought your last comment that we really must understand the attacks better before we can have the countermeasures. I was wondering, can you articulate the fundamental problem in hardware that causes these Rowhammer-like attacks?
I think the problem that exists in hardware is known to the DRAM vendors for quite a while now.
No, not DRAM. I mean, broader than DRAM. What is the fundamental big class of problems that causes these hardware side channel attacks?
Yeah, in general, we always have a trade-off between optimization, in optimization between performance and security. And the problem in IT security is that we don't optimize towards a physical boundary, towards a physical law that exists that prevents us from optimizing further, but we're optimizing with I hope so, with security in mind. And the problem now is that the adversary doesn't stick to its boundary that we intended to exist, or that we thought believed to exist. The adversary pushes the boundary more towards us and changes what it is allowed to do. So our previous assumptions about what the adversary can do might be wrong over time. And I think that's a problem. We need security mechanisms that we can, at a later point, adapt so that we can cope with a stronger adversary later on.
And so as we go to the last question, I'll just also answer that. There's actually a workshop that will be happening this summer with position papers due on June 1, just one-page position papers. If you search for the CCC Embedded Security Workshop, not the Chaos Computer Club, but a different CCC, the Embedded Security Workshop, a lot of these fundamental questions will be discussed. Our final question.
Yes, so Alex Gantman from Qualcomm. So I couldn't resist, since you set it up so well, Daniel, but your point about needing to develop proper long-term mitigations based on real understanding of attacks. So do you feel that the current disclosure practices adequately incentivize proper development of countermeasures over immediate short-term fixes?
It's difficult to tell. I think currently there's a lot of things changing, but in general, I think we've seen it in other areas. Bug bounty programs solve a lot of problems, or reduce the number of bugs in products, but I'm not sure that they necessarily improve the software quality on a long run. So the question is whether we are going the right direction here in hardware security. It's difficult to predict the future, right?
All right. Thank you, Dan. Now we have one, oh, thanks first.